Microsol, for inviting me to share this with you. It's a topic that I'm really excited to share with the industry. I want to set some context, a little bit of context of the stage. We're growing rapidly. By 2050, there will be 10 billion people that live on the planet. That's over 30% of our current population, and we're going to get that 30% in over 30 years. 75% of those people will be urban dwellers, and 95% of those 10 billion people will live within 1 day's travel of a city. Half of them are going to be in the middle class or moving into the global middle class. They're going to want a better lifestyle. They're going to want to purchase more cars, cell phones, washing machines, that new iPhone XS Limited that just got announced yesterday, refrigerators before. So, and what that ultimately means is we're going to need twice the energy that we use today to run all that. So we're going to need to find new, cleaner sources of energy and more efficient ways to run everything. And then when we think about the architecture, engineering, and construction sector, buildings, what we make, what we design, they're a massive, massive factor in terms of energy consumption. About 40% of global energy production, about a third of global greenhouse gas emissions, and about 30% of that energy in buildings is wasted, costing American businesses about $60 billion per year. And when you think about what that main load is it's the systems that serve the building. And really to get there, we need to reduce the amount of energy those systems need to overcome. For anyone who was at Autodesk University last year, our CEO, Andrew Agnos, got up on stage and he's made sustainability fundamental to the core vision of Microsoft. We understand there's an inevitability of more. There's going to be more people, more products, more goods. At Autodesk, we want to enable designers and people who make things. It doesn't even have to be buildings. It could be a television or a product or something that you have in your house. We want to make that better, and by using less resources. And on there is a quote from my boss, our VP of Sustainability, and looking at how the architecture of 2030 and how the AIA is helping architects. So something really important to think about. So when we think about sustainable design, we think about building performance analysis. And there's performance targets, and those performance targets can come from code, or they can come from a program that you're signed up for. Let's say you're pursuing LEED certification or living building or the WELL standard. And when we start to think about our buildings, we want to look at massing. We want to look at the building form. We want to look at how it's oriented, how the sun plays on it, and then and the materials it's built from. And then the climate considerations. Where in the world are you building? How are things moving forward? With Autodesk Insight, it's a tool that allows you to take care of climate. So you can look at how the climate's affecting the building, energy. You can look at your heating and cooling demands, and also solar and daylighting. If you want to move to some of the other things that are that are thought of as very important in building performance analysis, you can look at the Revit MEP tools and computational fluid dynamics, and then other plugins that go into Revit, such as Tally, which was developed by an architecture firm, Kieran Timberlake, which allows you to do a life cycle cost analysis. So let's talk about one thing, and this came out Monday, I think Monday, September 11th, and it's hot off the press. And I think this is really important, since this is an AIA certified webinar, to talk about some things that they just put in. So they adopted some new rules in their guidelines, new rules and ethical standards for members. And the three things that they added in were equity in the profession, sexual harassment, and sustainability. While not in the umbrella of this webinar, the equity and sexual harassment are very, very key important topics, as we all know. But I really want to dive into some of the things they put in sustainability. And I'm not going to read these to you. The link's down at the bottom. You can just do a quick Google of their press releases. But when you look at this, they're starting to really talk about sustainability and really say, this is your job. It's your job to think about the earth you're building on. It's about thinking about the materials that you're using. It's about setting ambitious performance goals for greenhouse gas emission reduction, thinking about your water, thinking about your materials, think about the impact on the earth, thinking about climate change, and then ultimately members shall consider with their clients the environmental effects of their project decisions. And that's very, very important. And that's essentially how we're going to set the stage for today. So when we think about it, we have the AIA 2030 commitment. And the AIA 2030 commitment grew out of Architecture 2030, which was launched in 2005. And what they wanted to do is offer the community a way to publicly show their dedication and track progress towards a carbon neutral future. Annually, the AIA reports on the results of products reported in the portfolio by the signatories. Architectural firms will sign up and make the commitment to drive their carbon performance down. Now, in this slide, that commitment, it asks the adopters to report on the progress of their portfolio. So you're going to look at how you design your buildings in schematic, design development, construction documents, and look at how their performance are and measure them against the goals. So we now have about 7 years of data, and we can see the trajectory of the industry. It's going there, but this dashed line up top is where we want to go. There's still a lot of work to be done. Every year, the AIA produces a report, and one thing that is true every year, you find that energy modeling is key to meeting the 2030 challenge. But the sad fact is it's not being done on every project. But projects that are doing it are performing significantly better than projects that aren't. So really, when we think about things, we want to think about ways that we can do that to perform energy modeling easier, with really nice, accurate results at early stages in the process all the way through the process. So let's think about what energy simulation is. Energy modeling, it's a physics-based model that looks at the performance of the materials of the building that block heat transfer or cool transfer, the materials that you use for your windows, the materials that you use for your roof, and then also the systems that it takes to meet that design. But we don't need to work in the dark anymore, not even if you're not a specialist. And my background, and I didn't really go into this, I probably should have, I'm an architectural engineer. I spend a lot of time in the trenches doing very complex detailed energy modeling in eQuest and IES, doing computational fluid dynamic modeling. But what always is the frustration to the architect is that the specialists take time. It takes time, and it gives you 1 point in your design, and we'll get to that. But that specialization doesn't allow for fast decisions in the iterative process that you as designers are doing with your clients very early in the process. Let's talk about the new design process. Here is the McLeamy curve, very famous. Some of you may be familiar with it, but we'll walk through it really quickly. If we think about this black curve, the black bell curve, that's your traditional design process. Preliminary design through your schematics, design development, construction documents are kind of at the peak of the bell, and then you go down. Well, what you're seeing in the red line is as you move through the process, the cost of your design changes it goes up through the process. But your ability to impact, cost and performance goes down as you go through that process. So if you make a decision as you're starting to mass and site your building down here, it doesn't have a high cost, but it has a major, major impact. But you see these cross kind of in that middle of construction document. So what we're hoping to do is to evolve that black design process and shift it over to the side so that you're making many more decisions early in the design process, getting really high impact at very low cost. And you see that you're almost through the game before you're even starting to gain cost. So we're going to talk about a metric today, and we're going to talk about energy use intensity. And it's thrown around a lot. People are like, what's the building's EUI? What's it doing? Well, let's make sure that everyone understands what this is. This comes from the AIA Energy Modeling Guide. Energy use intensity can be measured at the site, which is where the energy comes to your building. Think about that power line that comes to your meter, or you can call it from the source. Now, the source, if you have a source EUI, and these are just fine points for people to know, that source EUI is all of the resources that it takes to create that power at the power plant, be it hydro, be it coal-fired, be it solar. All of the embodied energy that it took to get there, any of the transmission losses to get you to your building. So your source numbers are generally going to be higher than your site numbers. And what the energy use intensity is, if you measure the annual energy use over the whole year at either a site or a source measure, and then you divide that by the total building area. So it's going to be either in BTUs per square foot or kWh per meter squared. And these are some US national averages site energy use intensity. And then what the 2030 challenge is to drive these down. If you really want to dive into the data that they're pulling this from, if you have a project that's not typical, there is a survey, and I have a series of links that we'll be sharing with you at the end, but the Commercial Buildings Energy Consumption Survey. And if you ever hear people say CBEX, that's where this data comes from, and that's the database that they're using to set these targets. So let's kind of talk about the paradigm, the design process. So we have a goal, and we have an architect, and we're going to start in the concept world. And the architect starts thinking, takes his or her pencil and a napkin, because all of the great buildings start on the napkin sketch. And they start drawing some massing. And we even have napkin shapes here. And then they're thinking about the window to wall ratio. Well, this is going to have a beautiful view. I'm looking out my window at the Berkeley Hills. So it's going to have a beautiful view of the hills. Is it going to have shading? Are we going to need to, for occupant comfort, for glare, are we going to need to have shading that makes the building perform better, keeps that direct beam sunlight from being a heat load, but lets in that great light? What are the materials we're going to use? Are we going to spend a lot of money on the glazing because energy is very expensive here? Are we going to want operable windows? How are we going to do that? So when you think about this, it's a very iterative process. It's interdependent and it's progressive. But here is where it gets complicated. In addition to the architect, you have the engineer, your engineering partner. Your engineering partner is looking at your building and they're saying, well, okay, are we going to use LED lighting? What's the best system for this building? Do we have room for a mechanical room? Are we going to incorporate any renewable energies? And countless other decisions. But then you have the owner with their own set of criteria. They're thinking about comfort. They're thinking about maintenance. They're thinking about cost. We all know they're thinking about cost and what the occupancy of the building is, how it's going to be used. And what this is the whole design, use, make process. And it's all in there. And we're all iterating over these many things. And how do we know in that what is right? Is it the energy code? Are we using manufacturer's data, rules of thumb, or historical data? There's all these different things that we're using. We can also use, at this point, an energy modeling simulation. Then it gives you the idea, if we design the building this way and use these materials and we use these window to wall ratios, this is what our energy use should be. It's very precise, and it does look at the whole system. But it lacks in accuracy and it lacks in guidance because we're really looking at a single point at that point. So if you think about that, you're looking at a single model to make some of those decisions, but each of these players in the design make use space has about 3 to 4 scenarios. That's about 3 million possibilities. If they up that to 4 to 5 scenarios, we're now at 68 million possibilities. So if we do even 100 different model simulations or thousands, how are we going to get there? Well, we want to look at a new approach. We want to start thinking, let's embrace that uncertainty and let's have the range that's available. We can have a range from high performance to low performance in a series of simulations. We run a number of simulations taking that into account and do a product factor across all of those, doing some regression and sampling and scaling. So essentially we're able to take, by doing a number of simulations, creating trillions and trillions of options that you can then control with a slider to get an energy range. That energy range says, well, we're not really sure what we're doing as far as materials today. But if we keep it open, if we embrace that uncertainty, we know it's going to be within this range. And so for each factor, be it your glazing, be it your window to wall ratio, be it your roof construction, your wall construction, your building orientation, potential for renewables on the roof, you get a range. You can keep that very, very wide open. You can keep that unknown. You can keep that undecided. You can cut that down into a mid-range. We know that the budget on this project is going to let us, at least hit industry standard or if not better. Or we know that this is a budget project and it's not really pursuing any aggressive codes. Anything aggressive, we're gonna keep it at code minimum. So you might need to know that that's where you're going to be going with a factor in your building. Or you can say, this is pushing the envelope. We're going for net zero. We are tightening all the screws and we're going to sail this ship to winning. And then once you've known or picked something, let's say you know you're going to use a certain type of curtain wall, you move it to the triangle and you can lock that in. Now it eliminates the range and you know what that one very sound performance will be once you start to lock that in. And that's essentially what we're gonna talk about. We're gonna talk about Autodesk Insight, which is a plugin for Revit, part of the AEC collection. And what it allows you to do is to take models from any stage in the design, from very, very simple massing. You can take the massing shapes and start to get some actionable insights. You can start to get more detailed and move in there and lock in some certain things that you've already had discussions with the owner, and really look at how those energy ranges go. You know, if you start and you're at about a 24, and then you start to, tighten down, going from concept to concept into a schematic and to a detailed design. And what's interesting in the slide that I like to say is, like, when you're looking at just some concept massing, you can see as the building grows along the way through the concepts, it gets addition. You see that, your EUI is going up, and the range is from between 109 and 46, and the range here is from 62 to 28. But then when you get into a detailed design, you see that range is, between 60 and 32.8. So you can see there's a similarity across that design process that you're seeing. So it's not like even early when you're doing those early massing, you're not that far off from how it gets as you get detailed. So that's one thing that really lends to the accuracy of it. Given that this is recorded and you can go back to it over and over, we're going to go through some of how you would go through to set up and use Insight. So this will be hopefully serve as you give this a try, as you move through some of the self-guided learning references that I will provide, that you'll come back to this and look at it as a reference. So after installing the plugin, which you download at insight360.autodesk.com, you set your location. So what setting the location is, by clicking the location button in the Analyze tab, that allows you to access the weather and climate data. So if you know the project's exact address, you know the town, you know the city, it will go, once you're logged into Revit, it will show you the weather stations that are closest to your project. I know in my past of modeling, if my project was here, I would look at this weather station at one point in the analysis to get that C effect, but I would also look at this one too, just because you're kind of in between both, and it's really important because this weather station is going to take into account all of the damping of the ocean and the bay, and this one won't. So that's one kind of fine point. Each of the weather stations have the weather data, and it's hourly data, and it's averaged over 30 years. And what it does is it gives you the solar radiation directions, your wind speed, your air temperature, humidity, and these are the physics details that are driving the analysis. One fine note on this is if the ID starts with 59, they're the typical meteorological years, which we refer to as TMYs. And that's what we prefer. Anything that's a 53 or earlier, or 52, come from a much earlier set. So they're not as up to date. So you really always want to target that 59 TMYs. What this enables you to do in the beginning is you might want to see some solar analysis. Let's say you want to see what the annual photovoltaic potential is on your roof surfaces. You pick that, you click it, it brings up, it gives you what the potential PV production could be on that roof surface, and then also a chart. This gives you where solar energy hits. you can see that shading affects it and makes it a little less in certain areas of the building. So maybe if you, maybe those would be places that you would opt not to put it, and you'd put it on more of these slanted surfaces, avoiding some of those shaded areas. So that's kind of one of the first steps. There's many different things. This is the same data that goes into the Insight tool, but it gives you kind of your payback limits. You can set that. You can give a potential for coverage, and those are just the different study settings that you're able to run with that. One thing that's really interesting, and this is a kind of a finer point about modeling, and it's something to be aware of. Here's something where we've picked an area of the roof, and we wanted to look at 2 different days. And so in this, we looked at September 21st, dawn to dusk, and we looked at September 22nd, dawn to dusk. And something should stand out to you in those. The insolation, or the cumulative solar that hits that, is almost doubled on a different day. And what you see is that peak is different. So it's always remember when you're running studies, you could always, that it's important to think about, if you're picking a day, check some days around it and make sure that you didn't get a day that fell out and is simulated as a cloudy day. Some days are cloudy, some days are sunny. So it's really important. That's why a lot of times we want to look at an annual study. But that shows that in that weather file, it is showing that that typical meteorological year has some variation and some flexibility. You can pick whatever you want. Roofs, for example, when we just picked that, you would go in, you'd pick up whatever surfaces you'd want to click. They will go into an opaque state, and then you click finish up in your window bar, and that will select that surface. I'm not going to dwell on the daylighting. I have a lot of resources that I'm providing you for it, but there is the ability to do very robust daylighting analysis in there. All of the different tools for LEED v4, option 1 and 2 are in there. Also customizable studies. If you want to see solar access in a site, you want to look at illuminance or daylight autonomy. So looking at those foot candles, how they would fall into a space. This gives you the daylight autonomy. You can export that by rooms into a schedule. And then you can also look at ASC, or annual sunlight exposure, in the daylighting workflows. This is one part, so I'm just going to kind of make a statement here, so we know that as we move to the next slide. The daylighting studies are free up to a certain threshold. They're run in the cloud, and if you go beyond, if you're doing, I believe, more than 7,500 square feet, they do start to consume a bit of a cloud credit that you would need to purchase separately to enable future studies. And we can provide more of that detail if you want to, if that's of interest later. Any of the energy studies, any of the solar studies, you can run them till the cows come home, and there's no cost to you. That's a free tool that's included with Revit and the AEC collection. And in this is just in some of the lighting references in the back. It gives you, we've really, since daylighting analysis is a little bit more customized than energy analysis, and you really need to dive into that. We've put together a ton of best practices and a ton of resources that will be provided to you following the webinar to go deeper into that. So let's look at when we're doing the energy optimization. The energy optimization, Revit energy settings. So you'll click on the settings, and these, as I said, I want this to serve as kind of a, I'm going to do this, I'm going to try this on a project. You'll open up the energy settings, and this is the workflow. So you're going to always want to use conceptual masses and building elements. Why this is it allows you to take into account any shading elements when the algorithm creates the GBXML model from that. If you have any context buildings that are outside that you've modeled as shapes, so you say, well, I know there's a big tall building next to this that's going to be blocking the sun. I need to have that incorporated. That's one of the reasons we're going to want to use that. This is the analytical space and surface resolution. One of the powerful things about this tool is you do not have to have a watertight model that you can drop in a bathtub, that there's no leaking. You can have some surface gaps, and you can have some space gaps. It doesn't need to be perfect. You can draw a box and run analysis on it. So we always recommend to start with the default analytical space and surface resolution and refine as needed. Perimeter zone depth. We recommend if there's no mass, if it's just a mass model with mass floors, we want to say, yes, put about a 15-foot perimeter zone that zones the model out. So the east and west facades are being looked at in different north and south facades. But if you're detailed and you have some rooms in there and you have some windows that you're there, we don't recommend setting that, because that zoning is already been, you've done that work, you've done those rooms and set up those things. If you're unsure, it doesn't hurt to zone, but best practices are as we mentioned. There are some advanced options. You can pick a building type, and what this does, this goes into those kind of benchmarks and goes into that CBEX data and says, oh, they're building a multifamily housing, they're building an office, they're building a factory. This gives us the typical schedules that you're going to need. This gives us what the energy use intensity should be for code, let's say by an ASHRAE standard, and then what that reduction is that you're shooting for if you are going AIA or Architecture 2030. Room and space data. You don't need to have rooms or spaces in the model, but let's say you're going to be putting a very big data center in the basement of an office building because they're going to run it there. You might want to just load that up, because if you're talking about, you might want to make that space and give it the mechanical properties. So we do take into account the energy, the kWh load of that. Or let's say you're doing a healthcare and you know that it's going to be a radiological facility that's going to have a ton of MRIs, and you just know that from the beginning. You might want to just take into account before you're talking about energy use intensity, because otherwise what will happen is if you're talking to clients about it and not taking into account some of the equipment, later on down the road, when it jumps up drastically, they're going to say, well, why, you told me it was 40 and now they're telling me it's 130, and that's just going to be because of equipment load. So the spaces are where you can assign extra occupancy, lighting, equipment loads, etc. And we always recommend to disable the detailed element material thermal properties, especially when you're just getting started and nothing's really dialed in. A lot of times people are using, wall types that might be too thick, that aren't, thermally accurate, and we don't want to introduce that level of error. It's best to let the algorithm show you how a building can perform in range, rather than take garbage in and give garbage out, the whole theory on that. So when we create the model, why would we want to start a model in a detailed space when we can start there? We already showed earlier that you're not that far off in running it on a mass and running it on a detailed model. So you can make the massing with levels, you can do some automatic perimeter core zoning and glazing, and you can get some very fast, accurate learning from there. You can see those things. And that helps you to inform this detailed design. And then you can run that later and see what the impacts of putting in the shading, what are the impacts of having this, this outward atria space up at the top where it has a ton of glass. So in order to set the model, we recommend creating a 3D view and then isolate the key architectural elements used. And that's going to be what's important to run the physics on for the energy modeling. And you see in that list, it's the ceilings, columns, et cetera, all the way to walls and windows. So when you look at this, we recommend you want to look at things like this building pad down here that's not going to really play anything in the modeling, and you want to set that to non-bounding, because what that does is it cuts your space, and it cuts. Because the processing time is proportional, it's cubic. We create a cubic voxel model to do this. It's 3 times, it's times to the third power. So if the red box is 10 and you cut it in half, that half 2 to the third is 8 times faster to run the model when you kind of cut your space. What you want to do, I talked about the analytical surface and the analytical spaces. You want to just take a quick look. If you see, oh, someone just didn't connect that roof together, or that we need to pop that wall up, it's good to fix it right there when you're kind of looking at it before you create the model. If they're really big, so we said, let's say our analytical spaces was 12 inches, anything over 12 inches, it's going to not, it's going to not be good for the algorithm. With small gaps that are beneath that resolution, it's fine. What you're going to do then is you're going to click create the energy model, and then it's going to create that, and then you can look at, in the analytical surface, you can turn everything off. So here what we're going to look at is shade surfaces. And you see there's a lot of shade surfaces, and what happened is this is actually walls that weren't set to room bounding. So if we go back and we set those to room bounding, and then start to look at different things, exterior walls and fixed windows, you can see there's also some walls missing here. So there's obviously some gap. You can go in and either change your surface resolution, or you can kind of find where that big gap is. And it's kind of a significant area, so you do want to fix that. So you can reduce the resolution, and you can recheck the model. So here we cut it from 16 inches to 8 and 4 rather than 18 and 12. You see, by tightening that up, now we've tightened those walls down in there. We're starting to make a much more robust model. We check the shades again. We set those to room bounding. Those walls are no longer acting as shades. But we do see that there's some issues over here in this little tower. And when we look, there's that big gap there where the roof is not connecting in. Good to kind of pop that in, rerun it again. Now you see the shades are where the shades need to be, the windows are where the windows need to be, and the walls are where the walls need to be. And this is your energy analytical model. This is what we will export via GBXML to eQuest to run your simulations on. So we've created the model and we sent it up to the cloud. Now it's in the cloud. You'll get an email saying your model's been received. We're running simulations on it. And then you'll get an email that says, your model's done. Please click here to go into Insight. When you go to insight.autodesk.com and log in, everything's going to be put into this bucket right here, uncategorized. A new model by default goes into uncategorized. What you're going to want to do, we're going to, let's call it Project X, because it's a secret project. We're going to want to create a Insight, call it Project X. And then you have Project X over there. You open your uncategorized, you go in the 3 little hamburger dots here, you hit move, and it asks you where you want to move it to. We want to move it to Project X. Do we want to use energy cost or energy use intensity? Cost, yeah, as it says, cost is more tangible and represents value to the building owner. But I always went against energy cost because these are predictive models and they're not exactly what their energy bill will be. So you don't want someone thinking it's going to only cost me 56 cents a square foot a year to run my building. That's great, because that's if it's run perfect. People walk in the door at 8 and they leave that building at 5, if that's how you have your schedule set up. And we all know we stay at our offices much later than 5. So that's something to bear in mind. But you can click between them just by clicking the little icon here. It'll go between dollars per square foot per year to kBTUs. And when you go in there, you're going to see the benchmark. You're going to see that range. You're going to see the best you can make that building perform is all the way down here at 29.8. And the worst you can make it perform is at 103.8 kBTUs per square foot per year. An ASHRAE benchmark, if you're just going to code, you need to get it to at least 92 or below. And this here tells you where you are at the point of where the model is. We talked a little bit about the BIM setting and the energy range paradigm. If you're just coming in a massing model, there's not going to really be a BIM setting because it's just a mass. You're going to think about like the wall types. They could be any of these. But what the BIM setting is what the what is actually in the BIM model, or what is the default. Any of these are alternatives, and this whole thing is the range that you can do. And that building energy range, as I said, updates in real time as you move through the different selections and shows what the impact on your energy cost or energy use intensity are. What we encourage people to do at this point is explore that opportunity, embrace the uncertainty. If you have no idea what the HVAC system is going to be, you haven't even brought a mechanical, you haven't even solicited bids for a mechanical engineer. Leave the systems in the full range unknown, and then as you start to have those conversations, you can tighten them up. As I said, if it's a very aggressive building, you might want to think about what the high performance range would look like, a mid performance or low performance. Ultimately, that BIM setting. Or there's another single point. You say, we're really going to drive our plug loads in this building down here. It's going to be something that we're really important. If you take that other single point, for example, in a construction material, and then move it back, go back to your BIM model and change the wall type to that. So let's say you had modeled it with just a very standard CMU block, but then you said, I want to have more insulation on it. And you go back into the model and change that and rerun the simulation. You would take that other single point, would then become your new BIM when you ran it through. This is important to mention now. It does not change. Any changes you make in the web instance of Insight, where you're learning and understanding your building, those places do not talk back to the model. This allows, if you think about it, if you want to have someone be running an analysis, you don't want them hurting the design as they move forward, because you can be working out of the same model. You can set up scenarios, a saved combination of settings. So let's say you're in New York City and you have the really aggressive New York City building code. So you can set up a setting of New York City building codes where when you push that button, it'll change everything to at least that code minimum. So then okay, I'm starting from code. What can I do to go better than code? You set up those scenarios, you dial in different factor settings, and then you can click between, and this you see also high performance envelope, high performance lighting and plug loads, and high performance building systems. And this is looking at adding photovoltaics. So this is important when you want to march down. This is where we started. This is the code building. We did some work on the envelope. We added lighting and plug loads. And then we thought about the systems, and we talked to our engineering partner, and then added photovoltaics. And that's that very classic march down that you see all the time when you're talking about these different things. You want to use that model compare in settings. You can also look at that model, how it's gone along the way from schematic to detailed, and those are kind of energy bars. It gives you a bar chart so you can see how that was going. You can share this. You can, over in the little dial, you can set your unit, your currency, if you know the utility rates, how it's going to be sorted. You can share these insights, so you can send this to another team member. You can send it over to your mechanical team. You can share it with them and ask for comments on what system to use. That's just a very simple internal chat comment function that happens in there. And then you can apply those scenarios to the models. This is one of the greatest things I think that Autodesk did with the AIA 2030 commitment. We were very instrumental in helping to fund the DDX, the Direct Digital Exchange, so that you could just take the data, and instead of running a spreadsheet or going in and filling out all of this, is to go over, click again in the little 3 hamburger dots, and click Export Report to the AIA DDX. This enables you to have the work in the schematic design, click Report to DDX. You're gonna report that out to the DDX by setting up your DDX profile in your profile. So you'd email us, email 2030commitment@aia.org for your firm's key. So you'll get a firm key. Someone in your organization already has that. You'll click Report to AIA. Excuse me, I'm gonna sneeze. Sorry about that. You'll report to the AIA DDX, and that will take your project right in, the project name, where it's performing, and all those general details will be pre-populated for you to save right into the DDX. It makes reporting your project as simple as a click of a button, which is always what we want to do and how we want to think. So this really gives us a sense of where we are today with Insight. And I want to kind of talk about where we're going with that. What we're moving towards in the future is to start to have that conversation now with the mechanical engineers and the architects. We want the architects in the room to be able to send their studies of a building to the engineers and have it be just as simple of a tool, but profoundly accurate for the mechanical engineers to start doing systems analysis. So here you see taking the building and making a zone. So let's say we know we're going to zone this and we're going to put this on a certain type of system. And throughout the building, then assigning, for example, a VAV system, putting in your hot water and your chilled water and your cold water loops, putting in your different coils and all of that data. And then what the development that we're moving towards is then being able to take this out into Open Studio and really dialing in. Do we want to put an underfloor air system in here? Do we want to look at chilled beams? Do we want to run some parametric simulations on the impacts of that? Open Studio runs on Energy Plus, and we're going to be able to then put in very, very detailed systems. We're going to be able to say, this is what it would look like with an underfloor system. This is what it would look like with an overhead VAV system. And that's the coming soon. So right now we have the tool for the architects to make their early decisions, and that what we are pushing towards and moving towards is to have the engineers be able to make much more detailed analytical systems in the same tool.